Our next speaker is Douvropoulos, who will be telling us about recursions and proofs in Cataland.
Thank you very much. So thank you, everybody. I want to say I'm very happy to be able to speak here. I also want to say thanks to the organizers in particularly for bringing the Greek summer to UC Davis so I can enjoy feeling like home. I'm going to describe a long project that we have together with my hugely suave guest that I'm very excited about. I hope you're going to like it. If not anything else, it will involve the Catalan numbers. Catalan numbers is a fascinating sequence. It's fifth number, not the fourth, not the sixth. It's 42. 42 is the fifth number. It counts dig paths from 0, 0 to an n. It counts triangulations of a polygon, and it counts non-crossing partitions. Okay, so these are some of the many interpretations of the Catalan numbers, but those are going to be my favorite for today. And I'm going to come back to them in various ways, both in generalizations and in contexts in reflection groups. Now, there is a way to count Catalan objects where you refine and you keep track of a few statistics. We know, for instance, that if we count dig paths with respect to how many peaks they have, we get the Narayana numbers. But you can do something better. You can not only keep track of the peaks, but you can keep track of the vertical runs of the dig paths. So all of these 6 dig paths here, they have vertical runs 3 and 1. But I've grouped them, they have 2 peaks. The 4 of them here have vertical runs 3 and 1, and you don't care about the order. This is just a number partition. And the bottom 2 ones have integer vertical runs 2 and 2. So there is this really cool formula by Creveres, which is also a product formula. It depends on the partition in a weird way. It's just the number of parts in front in a following factorial, and in the denominators you have the symmetries of the partition. So in particular, you have 4 dig paths here, because 3-1 has 2 parts, but no symmetries, but 2-2 has 2 parts and a symmetry, so you get 4/2. And the cool thing is that in the same way that non-crossing partitions were counted by the Catalan numbers, you can count non-crossing partitions with respect to the sizes of the blocks. And you still have the exact same Creveres enumeration with a beautiful product formula that has the symmetries of the partition in the denominator. Okay? All right, so this is the refinement that we've seen. Okay, let's move on. So a lot of the things that I do, because Vic Reiner was my advisor, is having analogs of beautiful results in the symmetric group in reflection groups. So I'm going to give you a very, very brief reminder of reflection groups. I want to point out, if you like the symmetric group really, really, really much, I'm going to come back to it at the end. So this is an interesting talk for symmetric groups as well. Okay, so reflection groups are finite subgroups of a general linear group. They're generated by Euclidean reflections. I'm showing you the dihedral groups for 3 and for 4 over there. They have some really nice properties. For one, they're classified. You know, they extend the Veil classification. We have 4 infinite families, the symmetric group, the hyperoctahedral group, the type D, all of our 3 stickers, plus the dihedral groups. I don't know why there was no question, is there a dihedral case? But okay. We have 6 exceptional groups. So this creates this sort of tension in the world of reflection groups, where you can prove more theorems because you can test cases on the infinite families, and you can ask the computer to verify them for the exceptional groups. So you boost the theory a lot, but then you don't feel that you understand a lot of the theorems very well because you don't have a conceptual explanation. Okay? So this talk is going to be about the case-free proof for one of our favorite theorems. Now, reflection groups have presentations with simple generators. The product of the simple generator is a Coxeter element, and the order of the Coxeter element is the Coxeter number. Those things are going to appear in some formulas. Okay, so the formulas for the Creveres numbers, they were indexed by integer partitions. If I'm claiming that I have similar formulas for reflection groups, I have to tell you what an integer partition is in reflection groups. So if you start with a set partition, and you take the Sn orbit of it, that's what an integer partition is. You forget the numbers, and you only keep track of how big each of the blocks are. Now, a set partition in the symmetric group is just an intersection of hyperplanes of the braid arrangement. And that's something that you can do in general. Over there I have I cannot really see the red dot. Okay, so over there I have the type B3 arrangement intersected with a unit sphere. And all of these intersections are small flats. The 4 circles here are part of an orbit of this flat under B3, and this orbit is what I would naturally call a generalization of a cycle type or of an integer partition. Now, these things have other invariants that are related to them. Because flats are intersections of hyperplanes, you can take the interval in the intersection lattice from the bottom element until there, and that's kind of like a smaller arrangement. It has its own characteristic polynomial, and it turns out that these things behave very well. All of the restricted arrangements are free, the characteristic polynomials factor with positive integer roots, and those roots are going to be called the Orlik-Solomon exponents. So for every type, you have a collection of numbers, which I'm going to be denoting BIX, and they are the Orlik-Solomon exponents. They detect copies of the reflection representation, the cohomology ring of associated Springer fibers, so they have interesting interpretations as well. And for the symmetric group, they're just the first few numbers until the dimension of the flat. Great. All right. Are we ready to see the very cool formula that somehow generalizes the non-crossing, the Creveras numbers? Okay. So maybe you cannot see it very well. So I have here the non-crossing lattice for S4. And I have 14 non-crossing partitions, but below each of them, I have written an element of the symmetric group. So what I did is I just wrote all of the numbers of the parts, but I wrote them in order. So here, I got 1, 2, 4, and not 1, 4, 2, because 1, 4, 2 is not in order. And in this way, I have a canonical way to embed these non-crossing partitions into the symmetric group. Now, one would have to show that this is meaningful in many ways, and it turns out it is, right? Before we go there, though, it's natural to be able to count them. You can say, for an arbitrary reflection group now, I'm going to start with a Coxeter element. In the symmetric group case, the Coxeter element corresponds to this one-block partition. And I'm going to get everything below it in reflection length, in the order induced by reflection length. So this realization of the non-crossing partitions is a little bit folklore, but in some sense it goes back to Philippe Bian in the early 90s. If I do that, I can count all of the elements that are of a particular type. That would mean if you take the fixed space of that element in the reflection group, that would be a flat, that would have a type. But here it is the things that I have separated by colors, right? So all of these partitions or these elements of the symmetric group correspond to a type. If you want to count how many non-crossing elements you have of a particular parabolic type, you get a formula that resembles so much the formula for the Creveras numbers. So you have a product on top that has the Coxeter number, plus 1, minus those Orlik-Solomon exponents, which is the same as the minus 1, minus 2, minus 3 here. And in the denominator, you have a normalizer over a stabilizer, which is a true symmetry group of the flat, right? It's kind of like on the spot generalizes the beautiful Creveras formulas. And okay, I have an extra factor m here. The factor m is because apart from counting elements in the non-crossing lattice, we can count chains that start at a particular element. So the m chains here would be chains of length m that start at a yellow object, for instance. So we have this very, very beautiful formula that only involves invariance of the group, that counts something that on the spot matches the enumeration in the symmetric group, but this was proven in a case-by-case way 20 years ago. So Vic and Christos Athanasiadis and then Rhodes for the arbitrary M case, they calculated them for the infinite families, they asked the computer and confirmed it for the special cases, and we didn't have a good explanation why these objects have this really nice product formula that involves the invariance of the reflection group. So this is the goal of this talk. The goal of this talk is to give a kind of like case-free proof that does not rely on the classification and shed some light on why this thing is true on this open problem from the early 2000s. I want to point out here that the talk said recursions in Cataland. Why would you believe that the recursion is possible? Well, already in our standard way to think, one of the standard ways to think of the Catalan numbers is that they have the beautiful recursion that in the triangulation case corresponds to picking your favorite triangle, right, and triangulating separately the two polygons. If you try to prove the Catalan numbers using this recursion, you can do it, but it's a little bit difficult. So imagine now why it is difficult for reflection groups. You still have recursions like that. The Fomin-Didin recursion is one of those things, but you would have to prove it for these formulas that involve weird invariance of the group. You would have to have a cool way to put the Coxeter numbers and the Orlik-Solomon exponents together. All right. So the proof of this thing is kind of like broken into 4 papers, so I thought one slide would be sufficient. So I have some of my, our favorite objects here, but I have to introduce the isosahedron, or really its dual, the cluster complex. We discussed a little bit that the Creveras numbers have a generalization for the non-crossing lattice that has this beautiful product formula. Now, it turns out that there is a similar picture in the isosahedron. You can count faces of the isosahedron or faces of the cluster complex, and they have a natural notion of type, And the enumeration there is very similar. You have the same product formulas, but instead of minus the Ehrlich-Solomon exponents, you have plus the Ehrlich-Solomon exponents. There are many proofs of this. There's like a reciprocity result that's similar to Erhard reciprocity theory. So after introducing this, I want to briefly say the two objects are very compatible, and we have a separate set of recursions for each of them. There is a recursion on the chains that I'm going to describe a little bit, which means counting chains with respect to their kth element. There is a recursion on the faces, which is a double counting of pairs of faces. On one side, you count a smaller face. On another side, you count a larger face. These two recursions, on their own, are not sufficient to prove the whole thing, but we put them together, and we prove the recursions on the formulas, and that is sufficient. And to put them together, we have, like in an earlier paper, done this sort of refined version of the H2F transformation. And I wanted to mention this because this is cool. So the sum of all of the rank numbers for the non-crossing lattice is equal to the number of the vertices of the isosahedron. If you do the F to H transformation, you would see that 21 has to be 6 plus 2 times 6 plus 3, and 9 has to be 6 plus 3 times 1. You have this binomial coefficient here. You can break this thing and keep track of what each of these numbers represents. This counts the number of pentagonal faces, and each of those pentagonal faces can be broken via the 4, 3, 1 partitions here, plus the smaller partition with a coefficient that refines the binomial one. So 3 choose 1 is broken into this sort of coefficient 2 and this coefficient 2 here. And these are all the ways that you can pick a subdiagram of A3 that has 2 nodes. So Vic asked me whether there was an explanation about it, and this is a really good question. I wanted to share it. The point is that the cluster complex and the isosahedron, they're not balanced complexes, so you shouldn't expect to have a colored F vector, but you have something that's almost like a colored F vector. I don't know why that's true. That's part of why I have so many colors in the slides, so that you remember that I have a colorful problem. So let me say just a little bit about the recursion on chains. The recursion on chains is easy and canonical, and I'm happy about it because we proved it with the sort of techniques that I introduced in previous work with Guillaume Chapuis, so I think that those techniques are strong. The rest of the things, they're also really hard and beautiful, but they feel a little bit more technical. I think this is canonical. So you can count chains in a lattice by saying, okay, if you want to count chains with 10 elements, let's see what type is on the third element. So over there, chains with m elements, let's see what is the type of the kth element of the chain, and if it is type Y, let's keep it, write it down, and then the remaining R elements are like going from type Y all the way up to the Coxeter element. So in some sense, in a summation like this, on the right-hand side, you have smaller intervals, either intervals that end up in a smaller parabolic group that you already know are true, or intervals that start at a higher point that you can already prove. So similar to what John Ablaze was talking in his talk, when you have like a refinement, you have many, many things that you can count separately, you can move more easily in your inductions or recursions. Okay. Now, if you plug in the formulas for all of these Creveras numbers, and you do a lot of non-trivial maybe stuff, this isn't direct, you get an expression like this that only involves Coxeter numbers. So this is the Coxeter number of the whole group, and this is Coxeter numbers for some parabolics. And this is an equation that's coming out of just a spectral study of an operator that I'm calling the W Laplacian. I'm not going to explain to you here how this comes, but I have an extra slide, so if you're looking for a question, you can ask me at the end, just saying. So if you want to think about it in the symmetric group case, when, for instance, X is the whole space V, and H is N, this is just a version of the matrix 3 theorem. What happens is that this sum over all flats corresponds to picking the connected components of your forest, and the product of the Coxeter numbers corresponds to, in each connected component, picking a rooted tree. Okay? So this is one of the ways to think about this, is as like a reflection group version of a matrix forest theory. And I put them all together, and it is equivalent to that and combines with the previous recursions. Here, again, 3 different, one recursion of the non-crossing lattice, one recursion of the isosahedron, another way to put them together, each of these things also for the formulas, and eventually it runs up. Okay, so that is most of the proof. I want to talk a little bit, I'm going to give you an interpretation that involves parking spaces. And I had to start with a diagonal action, it's going to be clear in a little bit. Okay, so like Heyman in 92 considers a diagonal action on the set of 2 variables with a symmetric group. This is Heymann's world, Heyman conjectures, Heyman proofs. We have these beautiful numerological properties, right? The dimension of the diagonal covariance is n plus 1 to the n minus 1. As a reflection group module, they behave like the parking function, right? Each of the parking functions has associated an increasing one, and this corresponds to the dig paths, or you can see the labelings of the dig paths as parking functions. In some sense, the essence stabilizers of the parking functions are exactly the vertical runs of the dig path. So this comes back to our numerology for the Creveras numbers. Why did I start with the diagonal harmonics? Because if you have a group acting on X, you can also make it act on another copy Y and consider its diagonal harmonics. It's very immediate to consider diagonal harmonics on reflection groups, but I wouldn't be able to tell you a priori what a parking function is. There is a problem here. The diagonal harmonics for reflection groups usually have a bigger dimension than the expected one, but Gordon actually constructed a quotient, and in the quotient, you have a bona fide parking space. We have an object that's now representation theoretically. It's as if we have our own nabla operator, but it's not really there because it only has one parameter. But the point is that now we have a representation theoretic way to think of the parking space. Okay, so a lot of the results that I'm doing really are decompositions of the parking spaces for reflection groups. And I want to remind you a few of the standard ones for the symmetric group. So for the symmetric group, if you take the nabla operator and, okay, I'm sorry, for me, I can barely do one gradient, so we start with 0 gradients. So you evaluate T and Q at 1, and you have an expansion with respect to the elementary symmetric functions, and the coefficients are those good product formulas, the Fuchs-Creveras numbers with symmetries of the partition in the denominator. This is an easy calculation. Now, if you evaluate at Q is equal to 1, then you still have elementary symmetric functions, but you can keep track of the coefficient because it's counting the areas under the dig paths. I want to point out all of these results kind of like they're subsumed by the Saflo theorem, but they were known before. So before Heyman had completed the work for the nabla operator and the diagonal harmonics, they would, I think, Garcia, Loerde, many people had shown that this thing is true by doing a combination of recursions, one on the representation theoretic side, one on the combinatorial side. And those were non-trivial results. And another one that I haven't seen in the symmetric group literature, so I've seen it in Vic Reiner's and Eric Somers' work. So if you expand the T is equal to 1 over Q evaluation with respect to the modified whole little polynomials, you get this very cool Q version of the Fuchs-Creveras numbers. Now, okay, I have enough time. I pledge $42 to whoever, in any sort of nourishment, liquid or not, to whoever helps me prove this with plethistic notation, because I tried and I cannot do it, and I know that this has like a plethistic formula. When I get a tenure track position, it will retroactively go to $132, but for now it stays at $42. So the idea is that we can do for the parking spaces in reflection groups a similar setting, and we have a few decompositions. Instead of elementary symmetric functions, I have the induced coset representations. Okay, these were supposed to be the homogeneous symmetric polynomials, but we tensor by that in these spaces. It's easier to have the formulas. So the Creveras numbers for the reflection groups now appear as structural coefficients for the coset representations. And the results that I've been talking about is to give a combinatorial interpretation of those things, the very beginning of something that will lead to a Saflo conjecture, right? Now, there are two that we know. One says that, and here this is more for the experts, I'm assuming, the coefficients of the coset representations are M chains of root ideals, of order ideals in the root poset under certain conditions. And what we proved, what is the main result of this talk, is that another way to think about it is the coefficients of the coset representations count M chains in the non-crossing lattice. Now, most people think of these things in Coxeter-Catalan combinatorics as the non-crossing versus non-nesting problem. Since these two coefficients are the same, why not find a bijection between these two natural objects, chains of order ideals and chains of non-crossing partitions? Our proof cannot do that because it's kind of like very linear in a sense. It cannot bring it down to a bijection. But I think it's good because, and this is a little bit unclear still because we don't have that much theory for the parking spaces, but it seems these decompositions are much more compatible with the gradients than the decomposition on the root ideals. And I can say a little bit more about that. So the last thing that I want to discuss is that the main kind of like pushing power of the theorem was that there was a decomposition that explained how to break a chain of M elements into a part that has K elements and R elements. And like people are asking me often, like, what is the version of that for the symmetric group? And the symmetric group is kind of simple. It's just expressing the nabla operator with the square of the smaller part, like nabla to the r, all the way until going to the m. And it has an easier proof. The nabla operator, when you evaluate one of the variables at 1, it's a commutative operator. But it's very difficult to, it's difficult to prove that the nabla operator at 1 is commutative. So it's somehow a lot of things are involved here. What you would do combinatorially here is that you have a chain of length m or a dig path of slope m, and you want to break it into two parts, and one has slope r and the other has slope k. So I did a construction of that using a laser idea, which I think does not exist in the literature. It might be easy to get it from work of Armstrong, Williams, and Brendan, maybe. You should tell me if that's the case. Anyway, so this is how it is. You take a laser of slope 2, you break your path into two components. The red laser things become the vertical runs of slope 1, and the remaining ones are the slope 2. This is good because this is a graded version of my previous decomposition theorem. I would like to be able to do that for a graded version of the decomposition for reflection groups. I would like to be able to use Galassin, Slam, Strand, and Williams' version of the braid varieties to prove a decomposition there. Trin said that it could be possible, but I don't know about it yet. I would like to have combinatorial models for a full QT grading. This is somewhat more recent advances involving the affine Springer fiber of the group. All right, that's it. Thank you very much.
Questions for Theo?
Can you say something about those W Laplacians?
Excellent question. Thank you very much. So there is a way to, yes, the question was, can you say anything about the W Laplacians? So the W Laplacian is an operator that you can, the W Laplacian is an operator that you can construct in the endomorphisms where you take the sum over all roots and you take an inner product with your element and the co-root, and this is a sum of rank 1 operators, and it is central because you're summing over all the roots, so it's easy to calculate its behavior. In particular, its determinant is going to be h to the n, and that's equivalent with a very nice formula that says hn is 2 times the number of reflections. This is really the graph Laplacian when you have it as the incidence matrix times its transpose, because this is the incidence matrix and this is the transpose. If you write down the characteristic polynomial of the Laplacian, easy linear algebra will tell you to break it over all subsets of roots, and only the linearly independent ones survive. And if you group them together with respect to their span, you're going to have this sort of decomposition over its parabolic flat over its flat. And that's exactly when you take the determinant in its part, that's exactly the formula that we wanted. So a parabolic expansion of the spectrum of the Laplacian is exactly the formula for the Coxeter numbers.
Other questions?
What did you want me to ask again, Theo?
Yeah, I was going to say, I think maybe this is a bit of a basic question, but I know, so like you're sort of considering these dig paths as sort of a type A sort of object corresponding to, you know, the type A vinyl group or Coxeter group or whatever. So like what are the corresponding objects in type B or in type D? Like are those just sort of variations of dig paths?
The best way, thank you, sorry. The question is there a combinatorial model, at least for type B and type D, of the dig paths or the non-crossing partition that looks like them? And yes, and I'm sorry Vic, I didn't mention it, so like this is what Vic essentially initiated in the mid-90s. There were versions of pictorial non-crossing partitions that had symmetries that made them type B-like, and other ones that made them type D-like.
Okay, so it's on the level of the non-crossing partitions.
In the level of the non-crossing partitions, that's right. Yes. You, Nathan.
Any idea how to get a rational non-crossing object in chain?
Thank you. That's a very good point. So Nathan is asking, is there any way to get rational non-crossing objects? So let me see in my secret slide. So the thing that I can do, if you expand this sort of Laplacian-like recursions, what is really happening is that they're telling you how to act by shifting by 8. So if you have an object for rational non-crossing objects, these recursions will tell you what happens when you shift by an edge or when you multiply by a full twist. That's the thing that I can do.
All right. Well, let's thank Theo again for the great talk.